As we just discussed, to optimize your transfer step, you will have to adjust current and voltage and make sure you're keeping temperature under control. But there's more to it than that. For example, you may need to adjust your transfer buffer composition. On the science section, Darren just talked to you about the role of methanol on your transfer buffer. So methanol shrinks the polyacrylamide gel, and it also strips SDS from your proteins of interest. What that ultimately means is that in the presence of methanol, it's easier for proteins to bind to the membrane, but it's also harder for them to elute from the gel onto the membrane. So depending on your proteins of interest, you'll probably need to adjust the percentage of methanol on your transfer buffer. The Towbin buffer, also known as the Tris-glycine buffer, typically has 20% methanol. But if you're going to look at proteins that are very big, you may want to adjust that concentration for something between 20 and 5%. If you're looking at small proteins, you will probably want to increase the concentration of methanol in your transfer buffer, something between 20 and 40%. Now make sure you do those adjustments slowly in increments, baby steps for that. You want to make sure that you find the perfect buffer composition for your particular target of interest. Don't forget to take into consideration the other variables of the transfer step. If you change the percentage of methanol in your buffer, it's very likely that you'll also need to change the length of your transfer and maybe even the current or voltage that you use for that step. In the science section, Darren also reviewed the role of SDS in the transfer buffer. So SDS is very important because it helps maintain the proteins denatured, and it also gives them a negative charge so that they can be transferred with the aid of an electric current from the gel onto the membrane. Therefore, we can consider that the presence of SDS helps proteins to be eluted from the gel, but at the same time it's going to make it harder for them to bind to the membrane. Ultimately, what that means is that if we have too much SDS on our transfer buffer, those proteins may leave the gel but never bind to the membrane. They may precipitate before that happens. What that ultimately means is that they might fall to the bottom of my transfer tank before they even have a chance to bind to the membrane. So if you're going to transfer a large protein, you may want to add a little bit of SDS to your transfer buffer, probably something between 0.1 and 0.25%, so that it's a little bit easier for the proteins to elute from the gel. However, if you add too much SDS, they may never bind to the membrane, so remember to take baby steps on that. In addition to that, when we add SDS to our transfer buffer, we're going to have an increase in current and therefore an increase in temperature. So when we add SDS to our transfer buffer, we need to make sure we do everything we can to keep that system cold, make sure it doesn't overheat. The Towbin or Tris-glycine buffer is still the most widely used transfer buffer, but you really do have a lot of options to help you optimize your transfer conditions to your particular target of interest. Especially when we have to extend transfer times, the Tris-glycine buffer may not be your best option since it tends to lose buffering capacity as heat increases throughout that prolonged transfer. So for example, if you need to perform a long overnight transfer for a large protein, it may be a good option to use a CAPS-based buffer. So again, there's really a lot of options to help you optimize your transfer efficiency. I understand that can be a little frustrating. There are so many things to take into consideration and so many different options that you can use. But on the plus side, that also means you have a lot of flexibility. So it may take you a while, but you will be able to optimize that transfer so that you can see your target of interest.